right ahead, because this is the beginning of the foundation for infinite series, which is a big topic in Calc 2. Kind of the hardest topic in many people's opinion. Hardest topic in all of calculus, according to many.
Hey, at least that means this is the hump.
It's the hump.
Yeah.
It's true. It's cool. Infinite series are cool. Super important for engineers. So let's talk about this foundational idea. Let me ask you a question. Do you think it's possible to add an infinite collection of positive numbers together and get a finite result? So you've got an infinite collection of positive numbers. You want to add them all up. Is it possible for that to be finite?
I feel like this is a trick question. The answer is going to be yes.
Of course it's going to be yes. But your instinct is so intensely telling you it can't be true.
I mean, I guess if it goes both ways.
And as soon as I show you this, you're going to say, oh, God, of course it's true. I knew that all along, but I never looked at it that way. So if you look at 1/3, isn't 1/3 the same as this repeating decimal forever and ever and ever? And isn't it true that this repeating decimal really is a collection of positive numbers that are added together? Right? So this is a collection right here of positive numbers that are all added together, and the result is finite. So that is the first thing we have to adjust in our perception of numbers. When we're adding an infinite collection of positive numbers, you can in fact have a finite result. And any of these decimals, there's lots of them. If we look at, okay, I'm going to do it. You're not going to like it, but I'm going to do it. So here's another one. That number on the right is 0.9 bar. 0.9 bar is the same thing as 1. 0.9 repeating is the same thing as 1.0. These are the same number. Decimal representations of numbers are not unique. If 1 and 0.9 repeating were different, then you would be able to measure the distance between them. And you cannot measure the distance between 0.9 repeating and 1. Like any number you give me and say, hey, this is the distance between them, I can show that that's false. Because you can go further and further out in the 0.9 approximation. So they are the same number. 1 and 0.9 repeating are the same number. So once again, we see that, oh yeah, there is an infinite collection of positive numbers that are added together, giving a finite result. So this is the crux of improper integration, and it is the crux of infinite series. That's all we do with infinite series is try to figure out when an infinite collection of positive numbers converges, in other words, it's finite, and when it diverges, in other words, it's not finite. That is improper integration and infinite series in a nutshell. Okay, so now that we understand that you can have an infinite collection of positive numbers add up to a finite result, let's look at this geometrically. So this integral here is an improper integral. So it's improper because we have this infinity up here. You all know from Calc 1 that a definite integral goes between two constants. Infinity is not a constant, so that does not count as a definite integral. So that's an improper integral. It's improper. There's an infinity up there. And you also know an indefinite integral has no limits of integration. It's just a family of antiderivatives. So This is an improper integral. Geometrically, we look and it's the area beneath this curve from a to infinity. Okay, we can't integrate from a to infinity. You can't plug in infinity, so it's not a definite integral. So we need another approach. Here's our approach. We go with a limit approach. So we are going to create a definite integral. Here is the definite integral that we are creating. We're going to pick b. Imagine b right there. So this b, if we integrate from a to b, that's a definite integral. This result is going to be, right in here, this is going to be a function of b. That'll be a function of b. All right, b is moving, b is moving around. This will be a function of b, and then we take the limit as b goes to infinity. So the idea is that we are going to get a function of b that represents this blue area here, and then we're going to just take the limit as b goes to infinity. We know how to take limits. So that's going to be the idea. You can do the same thing if your tail was to the left. The word that we use to describe these pictures where the tails go on forever, those regions are called unbounded. So an unbounded region goes on forever, but it can have finite area. Because when we're thinking about area, we're thinking of adding an infinite collection of rectangles that have positive area. We're just adding up, this kind of thing. So it all depends on what these look like. One necessary condition is that these individual, if you think of them as rectangles, these individual numbers have to go to 0. If those numbers don't go to 0, your area would be infinite. Your infinite sum would be infinite. For example, if you add 0.1 plus 0.1 plus 0.1 forever, that is going to be infinite. Right? So it's necessary that the terms go to 0. There's no way to end up with a finite area or a finite value for that sum if the numbers that you're adding together don't eventually become insignificant. Right? They've got to get to 0, or it's going to be like blowing up a balloon. Eventually it's going to pop. But if you start adding minuscule numbers together, then you can still have this infinite series that adds to a finite result. So that is a necessary condition, but not a sufficient condition. In other words, just because the terms go to 0, that's not enough. The classic series that we will look at this semester is called the harmonic series, and we will show that the harmonic series diverges. In other words, it doesn't converge. In other words, the collection of all those numbers added together is not finite. So these numbers are going to 0, but they're not going to 0 fast enough. So that's our whole goal, is to figure out, what does it mean? Okay, they're going to 0, but what does it mean for them to go to 0 fast? So we have to analyze that and figure out, is there a threshold is there a threshold that these have to follow in order for it to be finite? And yeah, there is. And so that's what we're going to investigate. We're going to try to figure out what it means for them to go to 0 fast, or fast enough for it to be finite. So this diverges. Just because they go to 0 is not enough. They definitely have to go to 0, which means it's necessary that they go to 0, but it's not sufficient. It's not enough. Just because they go to 0 doesn't mean it's going to be finite. Okay, so this is the more intuitive case, the right-hand tail. The left-hand tail is similar. We're going to integrate from negative infinity to 0. Oh, that's improper. It's improper. So we're going to create a definite integral here, just like we did above. So definite integral, that we know how to integrate. And as soon as we do this definite integral, this b is a variable. The b is changing, so that's going to create this right in here. This is going to become a function of b. And then we take the limit of that, function of a in this case. I said that wrong. Let me restate that. Because in this case, the a is what's moving, right? The a is the variable part. The b is going to be a fixed constant right there. So when they do a left tail, they let a be the variable. And when they do a right tail, they let b be the variable. So it looks like that. And then they let a go to negative infinity. If we have a double tail situation, you just have to split it somewhere and do them separately. And if one of them diverges, then the whole thing diverges. The area is infinite. You can't treat it as a single integral if you have two tails. You have to break it apart. So here they broke it apart at c. If we were breaking apart that integral, where would we probably want to break it apart? 0. Because that's going to usually be a great limit of integration. But they're just sort of generalizing here, and they're saying it doesn't matter where you break it apart. You don't have to break it apart at this high point. You can break it apart anywhere you want. We call that C, and then you'll have a right tail here, a left tail there, and in order for that bell curve to have finite area, both of the improper integrals have to be finite. So we will talk about these as horizontally unbounded. So horizontally, it's going on forever. We will also see that we can have vertically unbounded regions also. Vertical asymptote, like 1 over x. You have that kind of asymptote. You could have a vertically unbounded region as well. So those are the two types of improper integrals that we'll get. We're going to get the horizontally unbounded, and we will see the vertically unbounded in a minute. Okay. So let's see if we can do an example. So the strategy is to evaluate a definite integral from 1 to b and then take the limit as b goes to infinity. That's our strategy. So we're going to look at this function, 1 over x squared. 1 over x squared is the ski slope. And it looks like 1 over x squared, 1 over x cubed. They all look the same, right? They're just zipping down to the x-axis. At different speeds, 1 over x goes a little slower than 1 over x squared. And then 1 over x cubed goes even faster. 1 over x to the 4th goes even faster. So there is our function, 1 over x squared. We are going to create this area right here. We're going to create the definite integral right there. So and then we're going to take its limit. So we're going to take the limit as b goes to infinity of the integral from 1 to b, and then we're going to write that as x to the negative 2 dx. And so first I want you to be crystal clear that when we integrate this with this variable up there, we end up with a function here, right? We're going to get a function of b. Let's make sure that that crystallizes in your head. So we have this limit out in front, and then we do our integration here. This is a definite integral. We know how to do that. We add 1, divide by the new exponent, so we get that as our antiderivative. We're going to evaluate it from 1 to b. And we're just keeping the limit out in front. And then we plug in the b, and then we subtract off what we get when we plug in the 1. So here is our function of b, right there. That is a function of b. So if you have a letter, as opposed to a constant, in one of your positions for a definite integral, you end up with a function of that letter. And now we're going to take the limit as b goes to infinity. And that limit as b goes to infinity, what will that be?
1.
1. Because this piece right here, that's going to 0, right? That's one of the basic limits that you learn in Calc 1. If the numerator is a constant and the denominator is exploding towards infinity, the fractions are shrinking to 0. So this limit is 1. So that tells us that this unbounded region, so it's unbounded horizontally, this tail is going off to infinity on the right. That unbounded region is finite and has area 1. So the area beneath that curve is 1, from 1 to infinity. All right. One thing that I'll do throughout the semester, and you are more than welcome to do this too, right here, the subscript on the limit, if you put it in the first step, and then there's 10 other steps here, you don't need to keep rewriting it. I will then rewrite it for sure at the very last step where I'm actually taking the limit, but you don't need to put that subscript all the way through. If you have that word LIM, it's understood that if you've already established it, that it's going to be what you established it as. So you don't need to rewrite it all the time. So we're still just sort of intuitively thinking about this. We look at this curve and it's zipping down to the x-axis very fast. You usually can get a pretty good visual cue from looking at the graph, whether it's fast enough or not. But you have to do the math to prove it. Is there any step there that you have a question on? Any piece of that conceptually doesn't make sense or anything mysterious? Okay, so we have to keep this in mind. So 1 over x squared, we're going to look at a lot of reciprocal functions. That goes to the x-axis fast enough for convergence, 1 over x squared. So we've got that in our brain. All right, let's look at this one. So here we have an exponential decay, 2 to the negative x, 2 to the negative x, exponential decay. And we kind of already have established the intuition that an exponential decay function goes really fast, right? If something grows or decays exponentially, it's either going to infinity really fast or it's going to 0 really fast. So our intuition, hopefully, is that, oh yeah, that's probably finite. Exponential, and you can look at the graph. It looks like it squeezes down to the x-axis pretty darn quick. So our hunch is that this probably is going to converge, that area is going to be finite. So the area that we're finding, we're starting at 1 and going to infinity, so that's the area that we're going to infinity. We're going to pick a b right here. So we're going to integrate from 1 to b. We're going to turn that into a function of b, and then take the limit as b goes to infinity. All right. So the very first word every single time when you're evaluating an improper integral better be limit. You have to have a limit. You will not get points if you do not have that word. Or you'll lose points if you don't have that word. You may still get points, but not all the points. Super important right out of the gate. You see improper integral, the next word should be LIM. All the time. So we're going to integrate from 1 to b and let b go to infinity. And then we integrate 2 to the negative x dx equals, all right, so limits lingering in front. Now we have to remember how to integrate an exponential with a base other than e. Maybe we should go do a little review for a second. Let's go back in the Wayback Machine for a second. Let's suppose we have that function. Does anyone remember how to differentiate that function first?
Raise it to the e? Oh, wait. Oh.
Anyone remember off the top of your head what the derivative would be?
C to the power of x natural log of 2.
Perfect. All right, so the question is why, if you don't remember that. Remember that back in Calc 1, you did this type of thing, where you can take the derivative of both sides here. You're thinking about taking the derivative of both sides with respect to x. You can change the form of this equation, though, by using the natural log function. So if we take the natural log of both sides, so that we have the natural log of y equals, if we take the natural log of the right-hand side, we have that cool property that says the log of 2 to the x can come down in front as a coefficient. And now we can take the derivative here with respect to x of both sides. So we're going to take the derivative of both sides with respect to x. The derivative on the left, we have to use the improper integration. That's going to be 1 over y times the derivative of the inside, which is the derivative of the inside. Derivative of y is called y prime. And what is the derivative on the right? What would that derivative on the right be? No product rule.
I don't know that's right.
There is a product,
Yeah.
but we don't have to use the product rule. If it was 6x, what's the derivative of 6x? 6. That's a linear function.
Natural log of 2.
Natural log of 2. Right? Natural log of 2 is a constant multiplied by x to the 1. So that's just an mx, sloping natural log of 2 in this case. So there's our derivative, natural log of 2. All right, well, our goal is to find y prime, so let's multiply both sides by y so that we can get to y prime. What's y equal to? Go back to the beginning, 2 to the x. So 2 to the x, natural log of 2. So that is our derivative. That makes sense to everyone? So when we differentiate, we have this correction factor of ln2 that we have to multiply by. When we integrate, do you think we do something similar? Yeah, of course we do something similar. Do you think we multiply if we're integrating? We divide. So it's just like reverse chain rule. With chain rule, you multiply by the derivative of the inside. And when you do reverse chain rule, you divide by the derivative of the inside. And this is very similar. If you're differentiating a non-natural base, you end up multiplying by the natural log of the base. And if you're integrating, you end up dividing by the natural log of the base. So this will be, okay, so the integral of an exponential first and foremost is itself. And then we have to divide by the derivative of the exponent. That's the reverse chain rule part. We divide by the derivative of the exponent. Bless you. Then we have the, oh, it's not an e, it's a 2, so we have to adjust for the base being non-natural. So we do a division by a natural log of 2. So if you wanted to verify that this is the antiderivative for 2 to the negative x, you can use what we just did here. You would say, oh, the derivative of this is the derivative. We've got the constant part here, the negative 1 over ln2, but then the derivative of 2 to the negative x is going to be itself times negative 1 times natural log of 2 for a derivative. Natural log of 2's would cancel, and the minuses would cancel, and you get back to where you started. So you can confirm with that, oh yeah, that is the antiderivative. And then this evaluation symbol, 1 to b. So then we're going to have lim. We have a couple of choices here. You can factor out constants if you want, or you don't have to. It's really up to you. Sometimes factoring out constants makes it a little cleaner to evaluate the limit, but it really is your personal choice. As well as the negative exponent. Sometimes it's For many of us, it's easier if we get rid of the negative exponent and move things around. Usually it's easier to sort of see what's happening in terms of denominator going to infinity or to 0 possibly. So let's plug all this in first. So we're going to have, let's just write it first like this, and then we'll talk about different ways that we could do it. So let's just make sure we get all of this down first. So we're going to take the limit of all of that as b goes to infinity. That's where we're sitting. So does everybody agree with all of that? So I'm going to rewrite it and get that negative exponent down into the denominator just because I find that a little easier to think about. So we're going to have a minus 1 over 2 to the b times natural log of 2. And over here, if we bring down that 2 to the negative 1, we end up with that. So there we got rid of the negative exponents. We left the constants in. In this case, it's not too difficult to leave the constants in and see what's happening. So what is the limit of that expression?
1 over 2 ln2.
1 over 2 ln2. That is our limit. Because this first term, that's all going to 0, right? 2 to the b is exponential growth. 2 to a number that's going bigger and bigger creates a bigger and bigger denominator, which means a smaller and smaller fraction. So if the denominator goes to infinity, but the numerator is constant, the fraction values go to 0. Yeah, so that's finite, and that's the area. That is the area beneath that exponential decay function. Okay. So let's look at one that goes to negative infinity. So same idea, we are going to introduce, the book will call it an A. So to the left they use an A, to the right they use a B. So we're going to call that A. And then inside here we're creating a function of the letter A. And then we're going to let A go to negative infinity. When you look at the graph, does it look like this graph is going to the x-axis fast?
Not really.
Not really, right? There's a big old gap there. When we look at a graph, that goes to the x-axis fast, right? The x-axis and the curve become indistinguishable. So that's kind of a visual cue. Here it looks like, oh yeah, this gap goes on for a ways. So our hunch is going to be that it's not going to converge, that this area will be infinite. That would be our hunch. When you look at the power in the denominator is 1/3, right? So we've already seen if the power in the denominator were a square, we had 1 over x squared, that went to 0 really fast, 1 over x squared. 1 over x to the 1/3 is going to go slower, right? If you have an x in the denominator and the power is 2, 3, 4, 5, 6, 7, 8, 9, 10, that's going to 0 really fast. If you have an x in the denominator and you start getting down to x to the 1, x to the half, x to the third, x to the fourth, still going to 0, but it's going to go to 0 slower. Okay, so our integral is going to equal, so we will end up with the limit, and a is our letter of interest, so limit as a goes to negative infinity, and we have the integral a to 0, and I'm going to bump this into the numerator because that's a little easier to see how to integrate it. So we would have this. And that definite integral here this piece right there, that's definite, and that's what's going to give us this function of A. So that function of A is going to measure the area between A and 0. All right, so limit. Here we just do our regular power rule. So we have 2 minus x raised to the, we add 1 to the exponent, so we add 3/3, giving us 2/3 as the exponent. Power rule for integration says add 1 to the exponent, divide by the new exponent, so we divide by 2/3, which means multiply by 3/2. And then we have one more piece to this. We have the -1. We have the reverse chain rule. The reverse chain rule says if this is linear, which it is, power on x is 1, then we take its derivative and divide by that. Derivative is -1, so we divide by -1. So we're going to put a little negative right in front of that. Okay, so we added 1, divided by the new exponent, took the derivative of the base, divided by that. And this goes from A to 0. Okay. So here's an example where this -3/2, maybe it's easier just to pull that all the way out to the front instead of leaving that in there. And just like derivatives and integrals, constants can move through. So we'll just pull that -3/2 out, just kind of clean up what we're going to take the limit of. Plug in the 0, and we're going to get 2 to the 2/3 minus, so that -3/2 is out, so minus this expression with the a replaced for the x. So 2 minus a to the 2/3, close parentheses. So we're going to take the limit there as a goes to -infinity. Okay, so let's focus over here. Obviously, the 2 to the 2/3 is a constant, and we all know the limit of a constant is a constant. So that limit is just itself. Limit of a constant is a constant. What's going on over here? So to indicate this, I usually try to focus on the inside here first. And a is going to -infinity. So this inside piece is going to +infinity, right? 2 minus infinity, that's going to +infinity. We're going to agree with that? And then how about infinity raised to the 2/3 power? Where is that going? Infinity still. Right? If you look at any fractional exponent, in your mind, when you have a fractional exponent, you should be thinking of the bird wing. Right? So if you have some sort of bird wing like that, x to the half, x to the third, x to the fourth, x to the fifth, x to the 2/7, x to the 11/15. As long as that exponent is fractional, proper fraction, you got a bird wing in quadrant 1. And any bird wing is going to infinity as x goes to infinity. Who cares on whether it's going fast or slow? That doesn't matter. It's going to infinity. So that's that piece. Now we have this constant minus infinity. So this constant minus infinity, that whole part would be going to -infinity. All right, so little constant and subtract off something that's going to infinity, then that quantity will go to -infinity. And now we're ready for the whole limit. We take this piece here and this piece here, and we're multiplying those two together. So our overall limit will be positive infinity. So that's our overall limit right there. Now the thing that we have to be super careful with is some terminology here. This limit does not exist, right? A limit exists if you end up with a constant. So even though we say the limit of this integral equals positive infinity, it's not good notation, because that makes it feel like, oh, the limit exists and the limit is infinity. We just use this notation, and we need to be able to interpret it contextually here, that the limit still does not exist. The only way a limit exists is if you're going to a number. If you're not going to a number, it doesn't exist. When we write plus infinity here, this is just descriptive. It's telling us that the limit doesn't exist because the value is getting arbitrarily large. Right? We're not saying that the limit is infinity. You know, like you say, the limit is 5. We are saying the limit doesn't exist, and this is how it doesn't exist. It's getting, it's unbounded. The value goes up forever and ever and ever. Okay, so what that tells us then is that the area of this unbounded region is infinite. Yeah?
On a test, can we just like write d and e goes to infinity?
Yeah, you could write that. Yep. Mm-hmm. Yep. For sure. That is accurate. All right, let's look at one double tail. Double tail is pain in the tail. Always easiest, in my opinion, to split it at 0. Do you have to? No. You do not have to split it at 0. But having a 0 limit of integration generally makes life easier. So let's do this in 2 steps. So we're going to go negative infinity to 0 of this integrand. Plus the integral from 0 to positive infinity of the same thing. So that's the first step. If you have a double tail, you have to break it into 2. You cannot treat it as 1 and say, oh, let's put, you know, a here and negative a there and let a go to infinity. That will not work. Sometimes it will, but in general it won't. So we have 2 integrals that are both improper. So the next step then is to, we'll come down here, we're going to write this, the limit as a goes to negative infinity. And that's going to be a to 0. And let's go ahead and rewrite this denominator. We have a quadratic that doesn't factor. So we complete the square. So we're going to have x squared plus 2x plus 1 plus 4. We're going to peel off a 1. We complete the square by looking at this coefficient. Divide by 2 and square, you get a 1 to complete the square. So we'll pull off a 1 from that 5. And then our second integral, plus lim as b goes to the top, to infinity. And this will be integral 0 to b. And we have the same exact integrand, so we will rewrite it in the same way. So on the left, we are going to create a function of a. And on the right, we are creating a function of b. So we're thinking about b as being right there, a as being right there. Individually evaluate, and the only way this thing is finite is if both are finite. If one of them is infinite, the whole thing is infinite. So next step, we are going to look into this denominator. We're going to complete the square. We're going to have x plus 1 quantity squared plus 4. Similarly here, all right. I like to factor out the 4 here. You could do the x over a thing if you have it memorized. I would prefer to factor out the 4, so I'm going to factor out the 4 in the denominator. I like to memorize as little as possible. And I know that if I make that a 1, when this is factored out here, we end up with that. There is no 4 here, so we use our superpowers, multiply by 1. That 4 comes out in the bottom, right to there. Rewrite this as a single square. We've got that. And then similarly over here, we will factor out that 4. That comes to the front of the limit. And we're ending up with the same exact thing. So we've got that. Okay. Now we know that's an arctangent, you know? And if we do that factoring thing, we don't have to worry about is there a 1 over a in front or not. Doesn't matter. It comes out in the wash. If we can make that a trailing 1 right there, we know exactly how to integrate that without remembering anything extra. So this will be 1/4 limit. This is going to be arctangent of whatever is in the parentheses there. Divided by the derivative of what's in the parentheses. Right? Reverse chain rule. What's in the parentheses is linear, so reverse chain rule works. What's the derivative of the inside of those parentheses? Derivative of inside there is 1/2. So we have to divide by 1/2, which is the same thing as multiplying by 2. We're going to do that, and that's going to go from a to 0 plus 1/4 limit. Same thing here. We're going to get arctangent of that parenthetical quantity. Now we have to divide by the derivative of that parenthetical quantity. And this is going to go 0 to b. So, constant can factor out to the front of the limit. It can jump through the limit. Let's see. So in here, we will have arctangent of, plugging in 0 gives arctan of 1/2. Minus arctan of a plus 1 divided by 2, close. And over here, same thing. We can factor out the 2. We still have lim. And in here, we're going to have arctan of b plus 1 divided by 2 minus inverse tangent of 1/2. So we get that. All right. Let's pause there for a minute. Is there any stuff there that you're not sure about? Any issues? So we're looking at arctangent function. Arctangent function, remember, is a very cool function. It's one of the first functions you've ever seen that has 2 horizontal asymptotes. So the arctan function where are these asymptotes? What's the upper asymptote there?
1 or pi? No. Is it pi over 2?
Pi over 2, yes. And the lower asymptote is negative pi over 2. So arctan is sandwiched in between those 2 horizontal asymptotes. So this is as, let me get our thing straight, a goes to negative infinity. Let's jump that back in down here because now we're going to evaluate. And this one is as b goes to infinity. Okay, so first off, we're distributing the limit. The limit of this first term, that's a constant. Inverse tangent of a half, we don't know what it is. It's some irrational number. But it's a constant. Then, in here, the limit of this as a is going to negative infinity. So the inside of the arctangent is going to negative infinity. So we're trying to evaluate the arctangent of a number that's going towards negative infinity. What is that limit?
-1.
Negative pi halves, yes. Right, that lower asymptote is that negative pi
Yeah,
over
that's
2.
what I meant. It just, yeah, got it in my head.
So that limit is going to negative pi over 2. Similarly over here, this part is a constant, arctan of 1/2, some irrational number. This part, we can look at our graph to get a sense. So the inside, b is going to infinity, so the inside of arctan is going to infinity. So we're evaluating the arctan function at a number that's approaching infinity, and so that limit will be pi over 2. So this part's going to go to pi over 2. So we end up with, let's see, 1/2. Limit of a constant is a constant, so arctan of 1/2 minus pi over 2 gives plus pi over 2. Plus 1/2. And then over here, that's going to be pi over 2 minus this constant arctan of 1/2. So do we see that the arctan of 1/2s cancel? So we have a negative times a positive. So this is a negative 1/2 arctan. This is a positive 1/2 arctan. So those two things are going to vanish. And we are going to be left with pi divided by 4 plus pi divided by 4, which is pi over 2. So that is the total area underneath that bell curve. Some of you may be familiar with stats, and you deal with a bell curve in stats, and what they did was create a function symmetric about the y-axis so that the area of that bell curve is, for statistics, 1. Right? So the area under that bell curve, they created the perfect function so that that area would be 1, and that's how you do all the stat stuff off that bell curve. So we've got a bell curve here. Our area is pi over 2. All right, any piece of that you want to ask about? Yeah?
For that third one up, so it was at 1/4 and then it went to 1/2. That's just because of the 2 that you brought out, right?
That's right. So this 2 can factor through the limit here, and so 2 times 1/4 is going to give us that 1/2. Right. Yep. Exactly. Other questions? The double tail one is really just twice as much work. So we have finite area there. Look at that beast. Okay. So same idea. We're starting at 1 right there. We want this tail to the right. We're going from 1 to infinity. It's improper. We're going to sort of pick a b right there, so 1 to b. This is going to be a function of b in here. So we're going to get the area as a function of b, and then just take the limit as b goes to infinity to see if that expression has a limit. So, first word we always write down, limit, anytime we have an improper integral. Limit as b goes to infinity. We will go from 1 to b. And so there we're at. What technique of integration might we use here?
U sub.
With u equal?
X. 1 over x plus x squared plus 1.
So remember, whatever we pick for u, the derivative of that u needs to be present. So we want to let u be, yeah, if we let u be arctan, we're golden. So let's do that right here. We'll let u be arctan. And we're golden because we know that the derivative of arctan is 1 over x squared plus 1, 1 over 1 plus x squared, however you want to write it. Does not matter. And we see that its derivative is present. So that's what the key is for u sub. So we will have the limit of, so arctan is u. So we have u. And then dx over x squared plus 1, all of that is du. So we end up with that. And again, let's just use placeholder limits. We'll come back to x. We won't abandon x. So this will be limit of u squared divided by 2 with our whatever these placeholder symbols are that you want to use. So this will be 1/2 limit. We're going to take the u, replace it with arctan. Back to our x limits, 1 and b. Don't write that tan to the -2. That is inverse tangent squared. Then we'll plug in our limits of integration. So we plug in the b. We're going to have arctan of b quantity squared minus arctangent of 1 quantity squared. Taking the limit of all that. As b goes to infinity. So we come inside here, and the inside of this, where is the inside of that going? As b goes to infinity, arctan of b goes to?
Pi over 2
Pi divided by 2.
squared.
And then we're going to square it. Yep. So the inside, though, is going to pi over 2. And that's a constant over there. So let's see. So we end up with 1/2. So pi over 2 squared is going to be pi squared divided by 4. And then arctan of 1 is?
2 over 2.
So arctan is an angle. Anytime we see an inverse trig, we think angle. So it's an angle on the right with a tangent value of 1. So it is angle on the right with a tan value of 1. Pi over 4. So that pi over 4 is then squared. So we'll have that. Common denominator of 16, so we're going to have 4 pi squared minus 1 pi squared, so that's 3 pi squared. Divided by 16 times 2, that's 32. So there is our final area. So nice being able to make colors with this thing. When I first started teaching, we had like 3 different colored chalk. It was like trying to make colors. Such a pain in the neck. So much nicer.
Just a quick question.
Yeah.
Whenever we're doing the limits of infinities for arctangent, is it always going to be pi over 2 or negative pi over 2?
Yep.
Okay.
Always. So if we look at that graph that we had on the prior slide, that anytime we're dealing with arctan always looks this way. So arctan of x, as we go to the right, it approaches pi over 2, and as we go to the left, it approaches negative pi over 2. Yeah, always. And we're going to see that function a lot. That function shows up a ton. So having that image in your mind for arctan with that little sideways S thing is good function to have memorized. Yeah, it will always be that way. All right, let's see. Well, let's talk about, let me just get to the next slide and then we'll take our break. So this example of Gabriel's horn is a super common example that you see in Calc 2. We are taking the function 1 over x, and that's going to infinity. We're looking at the area beneath it, and we're sort of wrapping it around the x-axis, creating a solid object. So the volume is going to be found with the disk method. So I'll say one thing about it, and then we'll take our break. Gabriel's horn will be shown shortly to have finite volume. Okay? So we've got finite volume. So if you imagine this horn with finite volume, you can imagine filling it with paint. Right? It would take whatever the volume is, cubic units of paint. We are also going to see with Gabriel's horn that its surface area is infinite. Can you paint an infinite surface with a finite volume of paint? And of course, we would say no. But if the horn is filled with paint, it's painted. And that is Gabriel's paradox. So we have to think about that during our break. If we've got finite volume, you can fill it with paint. But if it's got infinite surface area, how can you paint it? But it is painted because it's filled with paint. So think about that over the break. How we can resolve this paradox. Think about it. And then we'll talk about it after the break.
Even though it doesn't.
One way or another.
Yeah.
Makes some sense. All right, so let's just look at the math real quick. Make sure we understand why the volume is this. So it's a disk method. So the idea is that if we pick a random x in here, random element, it's going to create a disk right there. And the area of a disk is pi r squared. Pi r squared. The function is the r, distance to the x-axis. So that's why we get volume is equal to that. And the integral of the volume so becomes this. And we already did look at this one kind of. We'll just go through it again though. So here we have a square in the denominator. And we saw that a square in the denominator creates a convergence because the terms are going to go to 0 really fast. So let's just do the math here though. So if we integrate this, we're going to add 1 to the exponent, giving us an x to the negative 1, which is a 1 over x. But then we also have to divide by the derivative, or excuse me, divide by the negative. We add 1 to the exponent, divide by the new exponent. So we get a negative. This will go 1 to b. This will be limit negative pi bths plus pi divided by 1. So plug in the b, plug in the 1, and then we're going to take this limit as b goes to infinity, and we will get pi. So there is the volume of Gabriel's horn, pi cubic units. So, okay, that is what it is. So that shows that we have finite volume. To show that we have infinite surface area is going to take us a little bit of abstract thinking here. Remember, first off, that this is the surface area formula. Remember that it's, let's see, 2 pi r ds, 2 pi r times ds, that's surface area. So 2 pi r again is the function. And then ds, remember we rewrite ds in terms of dx by doing 1 plus the derivative squared inside the square root. So the function is 1 over x, the derivative is minus 1 over x squared. So there's our surface area integral, 2 pi r ds. So I did it down here. Surface area 1 to infinity, 2 pi r ds. Now this integral is a mess. We cannot integrate that easily. There's no substitution that's going to work. And so what we are going to do is first, I didn't really even do much to this step. All I did was say, oh, it's improper, so let's do the limit. So this is the normal next step. Anytime we have an improper integral, let it go 1 to b, turn it into a limit. So we have a definite integral. Now here's what I want you to notice. Do you agree that this inequality is true? So let's take a look. We've got the matching limit, so we can ignore this part right out here. So just ignore the limit part. So forget about that. You can even forget about the integral, really, because the integral limits are the same. So let's just forget about all that. Let's just focus on the guts here. Focus on this and this. Do you see why that's true? Do you see that we have the 2 pi 1 over x? Those match, right?
But that one's being multiplied.
Isn't this always bigger than 1? Right, 1 plus 1 over x to the 4th is bigger than 1. So if you take its square root, it's still bigger than 1. So if we take away a part of this that's bigger than 1, we've shrunk it. All right? Everyone agree with that? So if we take away this piece is bigger than 1. So if we take something bigger than 1 and multiply it by a quantity, then that's going to give us a greater value. So if we have a, and we multiply a by 1.1, 1.1a is bigger than a. Right? So here is the a, and here we're taking a number bigger than 1 and multiplying it by a. This is bigger. All right, so that's just a kind of a logic argument there, since that's bigger than 1. So now, all that's left over here, when we look here at the limit, b goes to infinity, 1 to b, 1 over x. Forget about the 2 pi even. Just this limit right here. Let's look at that. Let's show that that's infinite. So we haven't done that one yet. Let's do it. So if we have the limit as b goes to infinity, so now the power on the x in the denominator is only 1. We've seen if the power is 2, it converges. Power of 1, we're going to see that it doesn't converge. So 1 over x is not going to go to 0 fast enough. What's the antiderivative for 1 over x?
Natural log of absolute x.
Natural log, absolute x, 1 to b. So we end up with limit as b goes to infinity, natural log of b minus natural log of 1. What's natural log of 1? 0. So that part is 0. And where does natural log of b go as b goes to infinity? infinity, because natural log is growing kind of like a bird wing. Doesn't go through the origin, but it is going to infinity. So this is infinite. So, so our conclusion here is that the surface area, which is equal to this, is greater than this limit that goes to infinity. So if this goes to infinity, that means this must also go to infinity. So that's how we can verify that the surface actually has an infinite surface area. So infinite surface area. So interesting, Gabriel's horn, finite volume, infinite surface area. There is if you look in the handouts, we have something that is analogous to this, where we have finite area and infinite perimeter. So it's called the Koch snowflake. The Koch snowflake, which you can make, if you look at our handouts here, I did all the math in one of the handouts here, right here, the Koch snowflake. So Koch snowflake is constructed by popping the middle third of each side of this equilateral triangle and putting in equal length replacements. And it goes on forever. It's a fractal. And we can show that the area is finite, but the perimeter is infinite. So same idea as it's one dimension less than the Gabriel's horn example. So Gabriel's horn, finite volume, but infinite surface area. Koch snowflake, finite area, but infinite perimeter. So we have all these oddball objects that we can start to look at once you're in Calc 2. All right, let's go to volume. All right, so here we have this weird-looking curve, which you've never graphed before in your life, and you never will graph in your life again. If you need that function, I will graph it for you. So we've got that region. We're going to bound it 0 to infinity. So our solid object has this boundary curve, and we're going to rotate it around the x-axis. We want to find the volume. What's your instinct? Finite volume or infinite volume?
Infinite.
Looks pretty infinite, right? Because that curve's not approaching the x-axis very fast. So it feels like it should be infinite. Let's find out. So we're starting at 0. So yeah, I guess I don't need to write that anymore. Okay, so the volume, if we rotate about the x-axis, we're taking a random x. That rotating around the x-axis is going to create a disk. So the volume of our disk is pi r squared. The radius is the function. So we're going to take pi, multiply it by this function squared. Let's write this denominator like that. It'll be easier to square it. So when we square it, the numerator just becomes an x, and the denominator becomes x squared plus 1 to the 2/3. So there is the volume. Volume of disk? Does disk have volume?
Nope.
What does it have?
Area.
Area. Yeah, that should be area of disk. Thank you. Area of disk. Volume is integral of area. So then we're going to come down here, and let's keep it all inside for a moment. This is going to be limit as b goes to infinity. We're going to integrate from 0 to b, the area function. So pi x over x squared plus 1 raised to the 2/3 power dx. So there is our improper integral rewritten as a limit of a definite integral. Limit of a definite. Pi can obviously come out to the front. What is the technique of integration that is going to work here? U sub is going to work great. If we let u be the inside of this expression right there, its derivative is 2x, and the numerator has an x in it. So it doesn't have to match it exactly, but it has to be a constant multiple of the derivative, which it is. All right, so let's go with that. We're going to say u equals x squared plus 1. du will be 2x dx. And that numerator just has an x dx, so we can divide by 2 in our head, or we can write it down if we're a little type A. So pi can jump in front of the limit. So we're going to put pi way out there in front. And then we have limit. And we're going to have new limits of integration. I'm going to put placeholders. I'll go back to x. I find with these it's a little easier just to go back. And let's see what's left. All right, x dx is du over 2. So I'm going to put the over 2 out in front with the pi, the over 2. So x dx is getting rewritten as du over 2. So then we have u to the negative 2/3. U to the negative 2/3 du. So we've converted it into an integrand that we can easily use the power rule for. We can add 1 to that exponent and divide by that exponent. So we still have a limit. We add 1 to the exponent. So negative 2/3, add 3/3, we get 1/3. Divide by 1/3, that means multiply by 3. This has our unknown placeholders. The 3 can come out to the front now, so we have 3 pi halves. Limit. Now let's go back to x. U is x squared plus 1, so we're going to have x squared plus 1 to the 1/3. X limits were 0 and b. All right, any cause for concern? Any part of that substitution that's not feeling good? So we plug in the b, we get the cubed root of b squared plus 1. Plug in the 0, 0 plus 1 is 1, cubed root of 1 is just 1. So that's where we're at. Where does that first term go as b goes to infinity? Infinity. Mm-hmm. Goes to infinity. And it's kind of what we were expecting, right? That's going to infinity. B squared plus 1 goes to infinity, and then 1/3 as a power. That's the bird wing again. So as we go out to infinity on the x-axis, b to this b squared plus 1 to the 1/3 also goes to infinity. Infinity minus 1 is still going to infinity. And so this will be infinity. So that means the volume is infinite. We can only do that with our bank account. All right, anything you want to look at there? So that volume is huge. Let's go vertical. So all of the improper integrals that we did so far were for horizontally unbounded regions. It is so simple to recognize when a horizontally unbounded region is improper because you see infinity in the limit. Right? You see it in front of your face. You can't miss it. When you have vertically unbounded regions, the unbounded nature of the region is hidden. Right? When you look at this right here, there's nothing giving it away that it's an improper integral. You don't see infinity in the limit of integration. And one thing in Calc 1 that they don't emphasize a lot is that in order for this to truly be it looks like a definite integral, but it's not a definite integral unless your function is continuous on the entire interval a to b. And that's not something you usually check. Like when you're doing integration and you have -1 to 3, none of us are plugging in the -1 and plugging in the 3 and checking to see if it really is defined on that interval. Right? We just assume that they aren't trying to trick us. Well, here, this is going to be an improper integral if the function is not defined at one of the endpoints or even at a point in between. And from the graph, we see that, this is not a definite integral because the function is not defined at a. There's a vertical asymptote. So what we do is the same idea. We're going to put a c in there, and we're going to make this a definite integral. So that will end up being a function of c. And then we are going to let c go to a. More precisely, we're going to let c go to a from the right. Right? We're not c going to a from either side, not a two-sided limit. It's a one-sided limit. This c is inside the region which is to the right of a, so we're coming into a from the right-hand side. So it's got to be a one-sided limit, not a two-sided limit. So this is improper, not totally obvious. Looks definite. Same thing here. This is improper. The asymptote is on the right. So here our limit is going to be as we approach b from the left. Same idea though. Our concept is that, we're going to build a definite integral right there. That's going to be a function of c. And then we're going to let c go to b. So that will be a function of c. Similarly, if we have a two-tailed thing, there's only one way to split the two-tailed thing. It's going to be, right down the middle. And what we'll do, though, is break it into two pieces. We're going to create that function of c, or whatever, the c there and d here, and then take limits. So you have to do it in two pieces. So let's try a vertically unbounded region. Vertically unbounded. So when I look at this function here, this function is y equals x squared, y equals 1 over x squared. All these reciprocal functions are going to look like slopes that are approaching both the y and the x-axis. We already did this one twice now, and we know that this horizontal tail is finite. The vertical tail is going to be infinite. And we're going to see this kind of whack-a-mole thing where as you increase the denominator's exponent here, it gets tighter and tighter and tighter to the x-axis, and it's going to pull it away from the y-axis. So let's show, we already showed that this is finite. let's show that the vertical tail is not finite, that it's infinite, that you're going to have one or the other depending on which, which tail you're looking at. So when you look at this, you now need to get into the habit of thinking about plugging in the numbers on this interval. This is only a definite integral if the function in here is defined at every single point on the closed interval 0 to 1. Oh, it's not defined at 0 though, right? So we know we have a vertical asymptote at 0. So this says this is going to equal the limit as c goes to 0 from the right, c to 1, let's make that x to the negative 2, dx. So 0 to 1, we're right in here, right? There's 1 right there. What we're doing is creating this c value that is, somewhere between 0 and 1, and we're finding this area as a function of c, and then we're going to let c zip over to 0 from the right. So we have to have that one-sided limit. All right, well, in terms of integration, pretty easy. Add 1 to the exponent, divide by the new exponent. So we add 1 to get -1, divide by -1. Let's write it as a fraction, so it's 1 over x negative. Limits of integration are 1 and c. So limit -1 plus 1 over c. This limit is as c goes to 0. Don't be fooled into saying, oh, the limit's -1. We are not letting c go to infinity. Right? All the limits we've done so far have been to infinity. This one is not, so be super careful. Limit of a constant is a constant, so that's fine. 1 over c as c goes to 0. What is that going to be?
Infinity.
Infinity, right? Numerator constant. Denominator is getting smaller and smaller. It's approaching 0, so that means the fractions are getting bigger and bigger. In your mind, you think 1 divided by 1, 1 divided by a 10. So if this is going to 0, 1 divided by a 10th, 1 divided by 100th, 1 divided by 1,000. So you imagine dividing by smaller and smaller and smaller numbers, that's going to make the fraction bigger and bigger. Divide by a 10th, and all of a sudden you're at 10. Multiplying by 10. Divide by 100th, you're multiplying by 100. So this part right here is going to positive infinity. And of course, if you subtract 1 from a quantity going to positive infinity, your limit is still positive infinity. So that shows us that that vertical tail is in fact infinite. So vertical tail is infinite, horizontal tail is finite. And this is going to be a pattern that we're going to see in all cases but one. There's one exception where both tails are infinite. With 1 over x, we will see that both horizontal and vertical are infinite. All the other ones, powers of x in the denominator, one is finite, one is infinite. So now let's look at these fractional powers of x in the denominator. Looking at the graph, you see that, oh, looks tighter to y and further from x. So this is going to be the opposite. We are going to see finite vertical tail and infinite horizontal tail when the power of x is less than 1 in the denominator. So let's do the vertical tail first. So vertical tail, we're imagining this thing. Let's see, we're going from 0 to 1. So we are going to build a function right here of c. There's 1. And we're going to approach 1 from the right. So this one is equal to the limit as c goes to 0 from the right, integral c to 1, Let's write that as a negative exponent in the numerator so that we can integrate easily. So this will become we'll pull out the 4/3. So add 1 to the exponent, divide by the new exponent, plug in our limits of integration. We have 1 to the 3/4, which is 1, minus c to the 3/4. And this is as c goes to 0. Okay. C to the 3/4. Again, bird wing. But we're not going to infinity. We are going to 0. So as when we think about this function right here, we imagine this bird wing. And as we're coming to 0, though, we're landing on the origin. So the limit of this is going to be 0. This piece right here is approaching 0. So we end up with 4/3. So vertical tail is finite. So that vertical tail is finite. That area, we just computed it to be 4/3. Let's confirm that with the horizontal tail, we get infinite. So we're going to let b go to infinity. Again, we're going to rewrite this so that we have a negative exponent, so we can use the power rule. So now we're going to, this one we call it c. So now we're going this direction. And that one we usually call b. And b is going to go to infinity. And let's just confirm. So we get x to the, add 1, so we get 3/4. Divided by 3/4 is 4/3. 1 to b. We'll get 4/3. The limit of b to the 3/4 minus 1 as b goes to infinity. B to the 3/4, again, it's a bird wing coming off the origin, quadrant 1. But now we're looking at the limit as b goes to infinity, so what will that limit be? Infinity. So we have infinite area horizontally. Infinite area horizontally. Let's see. I don't think I have another one on there. No. Don't want to miss. All right. Okay, so you all try this one. So, or is that one too hard? Let me see what the next one looks like. Oh, it does look. No, that's an integration by parts. Yeah, try this one. It's not that hard. So, let's set this groundwork up. We notice that it's an improper integral because at -3, we have an undefined integrand, correct? So we have an asymptote, vertical asymptote. So our setup is that we're integrating from -3 to 1 all the way over here. So we're imagining putting in our c somewhere here, and then we're going to create this region that will have area that's a function of what letter? C. Function of c. And then we're going to let c approach this vertical asymptote from the, what side?
Right.
From the right, yeah. All right, so set that all up and let's see what happens. And I can do what I'm supposed to be doing every single day. Taking a roll. Guy Cal is here. Kim is here. Marcus is here. Ethan. Was he here earlier? He's usually here. Sean is here. Alexander is here. Che, you've been on a long time. Caitlin is here. Stockton is here. Not here. Mason is here. Maxwell's not here. Where's he? Caleb, Sebastian, Couture is here. Eric is not here. Jesse is here. Will is here. Tyson is here. Are we looking for a finite answer or an infinite answer? So we should already know that it's going to be finite, right? Because the power on x is a fraction. So we've seen that for vertical tails, if the power on x is a fraction in the denominator, we get finite vertical but infinite horizontal. So you should be looking, you should know, your intuition should be built up enough by now that we are looking for finite. That's really helpful to guide you as you're going through it. It's really easy to screw up your limits if you're not sort of knowing where you're going. Anyone have an issue with that setup there? We're going to replace the lower limit with a c. We're thinking of our definite integral as going from c over to 1. And then when we do our integration here, this we can just use reverse chain rule, power rule, add 1 to the exponent, get a third. So we add 3/3, get 1/3, divide by 1/3, which means multiply by 3. So that's the power rule part. But we have one extra adjustment. That is a linear base, but it has a derivative that's not 1. So we have to take its derivative and divide by it. So we're going to end up with a half out in front. So divide by 2 there. So we can do it like that. And then this will go c to 1. 3/2 we can pull all the way to the front if we want. Plugging in the 1 is going to be 2 plus 6, which is 8 to the third. 8 to the third is 2. So we have that, and then we subtract off the evaluation of the antiderivative at the lower limit. So we get that. And then c is going to 0.
Wait, -3.
-3.
Shouldn't go to -3.
Oh, why did I put 0? Thank you. Yeah, I was just looking at that. I'm like, wait, the third root of 6. That's weird. Yeah, we are not going to 0. We are going to -3. Thank you. -3 from the right. -3 from the right. That's better. Okay, that looks much nicer. So whenever you're evaluating a limit at a constant, you just plug it in first. And if you plug it in and get a value, that's all you have to do. So we plug that -3 in. -3 times 2 is -6. Negative 6 plus 6 is 0. So that's all going to go to 0. All right. So that tells us that our final answer is 3. So that is the vertical tail. Vertical tail is finite. So we're starting to see our pattern emerging. All right, let's look at this funny looking thing. So our limits of integration are 0 and natural log of 3. Once again, it looks like a definite integral. If you were in Calc 1, you would just start integrating. But we now know that looks can be deceiving, and we see that if we plug in 0 right there, this is undefined. E to the 0 is 1, 1 minus 1 is 0, division by 0, vertical asymptote. So, same process here. Our upper limit is natural log of 3, which is right there. We are going to put in a c right there. And that's natural log of 3. And then we're going to let c go to 0 from the right. So our area will be, so this will be the limit as c goes to 0 from the right of c to the natural log of 3 of this horrible looking integrand. Looks terrible. Okay. So, any ideas? U sub.
Secant? Oh, no.
I'm not going there. That sounds scary. So if we do u sub, usually we let u be whatever's in parentheses, in the angle, in the exponent. The natural choice here is the e to the y minus 1. And you say to yourself, at least when you're thinking about whether to even proceed with u sub, you think about the derivative of u, and you ask yourself, is the derivative present? And yeah, it's in the numerator, right? Because the derivative of e to the y is itself. So it's actually way less scary looking than it originally may have seemed. So we are going to convert, and we'll just use some placeholders. So we'll use some placeholder limits here. And we're going to have u to the negative 2/3 times e to the y dy is du. Perfect. Way less intimidating than it looked originally. U substitution, a beautiful thing. So limit, we add 1 to the exponent, we divide by that new exponent. Right now we have just some placeholder limits. We want to get back to the original variable. We can factor that 3 to the front. So the original variable, we go back to y. So we're going to have u replaced with e to the y minus 1, raised to the 1/3 power. The y limits were c to ln 3. And then we're taking the limit. Well, we'll do that in a moment. So we have 3 multiplied by limit of, plugging in ln of 3, e raised to the ln of 3 is 3. 3 minus 1 is 2. So we have 2 to the 1/3 power minus the quantity e to the c minus 1 raised to the 1/3 power, close parentheses. And now we can take the limit as c goes to 0 from the right. So as c goes to 0, e to the 0, 1. 1 minus 1, 0. So that whole part's going to 0. So we end up with our answer. We have 3 times the cubed root of 2, however you want to write that. That will be our finite vertical area. Now this thing, not so obvious. It's not a power of x in the denominator. We've seen that our power of x in the denominator, if the exponent is fractional, we have finite vertical and infinite horizontal. And if the power on x is bigger than 1, x squared, x cubed, finite horizontal, vertical, infinite. This is not doesn't have quite the same intuition as the other ones. You could, if you wanted to think about the essence of these parts of the fraction, you can think of the numerator as e to the y, and this little subtraction of 1 is pretty trivial overall. So you could imagine this as being sort of e to the y over e to the 2/3 y. And if you were to simplify that, you would get what? Y minus 2/3 y is e to the 1/3 y. So you could kind of go down that road and say e to the 1/3 y is e to the 1/3 y exponential growth or exponential decay.
Decay.
So as this y goes to infinity, where does this go to?
That goes to infinity.
That goes to infinity, right? So, but when we're talking about a vertical tail, yeah, this is not helping much. It's not helping much. Like with the x's, you can really get a sense for what's going on by just looking at the power. Here, we would have to do a little bit of stretching to sort of try to make that work, and I'm not seeing a real obvious way. So if it's something that's not obvious, like powers of x in the bottom, you just have to do the math correctly. Yeah, when you look at that, I don't see anything that's jumping out as obvious to why it would be finite. I'm sure we could come up with something if we had to. All right, let's. All right, you all try this one. A little refresher, integration by parts. So this is the more straightforward type where we're letting b go to infinity. So we'll mix this up with an integration by parts. Get a little practice on that before our test in a week. Remember, worksheets are due tonight by midnight. We'll review all day Tuesday. Have our test Thursday and then go on spring break. How in the world? How is that possible already? Let's go. You know if you're stuck on something? Maybe I'll think about the last one while you're thinking about that. Oh, I just saw it on the last one. Let me just a quick side note on the prior one. When we get to right here, we are integrating 1 over u to the 2/3. There's where we see that fractional exponent that tells us vertical is finite. That's where we see it. After we do that substitution, here's where we can say, oh yeah, the power on the denominator's variable is fractional, so vertical will be finite, horizontal will be infinite. There's where we see it. I knew there had to be something in there. So it's after we do the substitution that it gets revealed. We're so impatient though. One of the things to think about with this one, you see that power of 2 in the denominator, which is telling you converge. It's telling you it approaches the x-axis fast. But you've got this little ball and chain, natural log of x, that is going to infinity. But it's going to go to infinity slow enough that it can't offset the speed at which x squared would go to 0. 1 over x squared would go to 0. But that's one of those, this is one of those wrestling matches that the numerator is trying to drag it away from the x-axis, but 1 over x squared is going to go to 0 so fast that it can't. That 1 over x squared is going to win. At least it looks that way. We'll find out. Is natural log of x strong enough to make divergence? When you do the integration by parts, where should the natural log go? U. It's got to, because that's a derivative we can take easily. It's not something that we can integrate easily. Whoops, UV. UV. UV minus integral of v du. That should be your first integration by parts step. Limits are 1 and b, uv minus the integral of v to u. That's right. 1 over x squared is x to the negative 2. It's going to be easier to integrate it right away. So here's where we get to the thinking. So before we talk about this limit, does everybody agree on the pieces that go inside here? Is there any discrepancies that you're seeing or came across? Does that all look good? Obviously, where does 1 over b go as b goes to infinity? Yeah, that'll go to 0. The question is, the one that should cause you pause is that first one. Natural log of b divided by b. Where does that end up as b is going to infinity? Say again?
0.
It's going to be 0. Do we know why? There's a rule that you should have learned in Calc 1.
Natural log of 1 is 0.
Natural log of 1 is 0, but if b is going to infinity,
As the denominator gets larger, the number itself approaches 0.
so then that's why we have to prove that. So that numerator is going to infinity and the denominator is going to infinity. So it kind of boils down to which one goes to infinity faster. If the denominator goes to infinity faster, it's going to force the fractions to 0. If the numerator goes to infinity faster, it's going to force them to infinity. And so there's a rule that you use back in Calc 1 called L'Hopital's rule. Like if you have, so let's go to x's, a little easier to think about derivatives. So if we have that function, and we want to take the limit as x goes to infinity of that, both top and bottom are going to infinity. And so then we have to do a different type of analysis. And L'Hopital's rule says that if both are going to infinity, you can look at the quotient of derivatives. So let's think about that for a minute. We are imagining these two functions that are forming a fraction. One is the natural log function, one is the identity function, y equals x. You can kind of think of two separate functions, a quotient of functions. And we think of the derivative as the best approximation for the function. So the idea behind L'Hopital's rule says, if you look at the quotient of functions, the quotient of functions should approach the same thing as the quotient of best approximations. Right? So if we take the derivative of each, not the quotient rule, but the derivative of top, the derivative of bottom, that quotient of derivatives should approach the same thing as the quotient of functions because the derivatives are the best approximation. It wouldn't be a very good approximation if it didn't approach the same thing. So the idea with L'Hopital's rule is that we're going to take the derivative of the top, the derivative of the bottom. So we get the limit of 1 over x as x goes to infinity, and that is 0. So we're using L'Hopital's rule right here. L'Hopital's rule. So a lot of times if we're using L'Hopital's rule, I'll just put some sort of mark right there to understand what we're doing. So if you have an infinity over infinity, L'Hopital's rule tells us what to do. And so that will in fact be 0 there. So this is going to go to 0, L'Hopital's rule. So that will be the area of this unbounded tail in here, right? All that. Has an area of 1. Crazy. Doesn't look like an area of 1. It looks irrational. Okay. Let's go to this summary. Try to summarize everything. So first, this threshold that we've sort of bounced around today is based on the denominator being just an x. If we get more complicated things, this doesn't quite hold, but we need to understand the basics here. If we have a power of x in the denominator, so we've seen that the threshold function is 1 over x. 1 over x is going to diverge both vertically and horizontally. So the black curve is 1 over x. So if we look at the black curve, it's going to, and if we go 0 to 1, the black curve, that's going to be infinite for the black, both horizontally and vertically. So 1 over x, infinite vertical and infinite horizontal. And then here is the whack-a-mole part, where we, why is that not turning off? The whack-a-mole part, let's look at the red. So the red, if we have a power that's a skosh bigger than 1 in the denominator. So 1 over x diverges both sides, but if we bump the power up in the denominator and make it just a skosh bigger than 1, so say 1.1, so the red, you can see as that power gets bigger than 1, it gets tight on x and loose on y. We're going to have convergence horizontally and divergence vertically. It's getting tighter to x, convergence, further from y, divergence. And if we go the opposite direction on the power on x, and we go a skosh under 1, so 0.9, that's the blue. If we go fractional exponent in the denominator, the blue gets tight on y and loose on x. So we're going to have vertical convergence and horizontal divergence. Everyone tracking? So fractional exponent, horizontal tail diverges, it's infinite. Vertical tail is finite. Power in x bigger than 1, horizontal convergence, and vertical divergence. We just have to try to keep that straight. So improper integration is vital in engineering. Improper integrals happen all the time in engineering. The most important improper integral that you're going to see initially is when you get to differential equations and you look at the Laplace integral. And the Laplace integral is going to be used. It's used a lot in electrical engineering. It's used a lot where you have functions that are discontinuous. And so you all have sort of pieced together that when you have discontinuities, it's a headache. If you have a function like a step function, if you're looking at electric pulses and things, you're going to end up with square waves and these waves that are going to be that are not going to be differentiable where there's those corners. And the Laplace improper integral, it's so fascinating. You can take this e to the negative st, and you can take a function that you can't do anything with in the xy plane because it's got all these discontinuities or points where it's not even differentiable. And you can convert it over to this Laplace domain, and that's what the S domain is. Instead of being in a T domain, you're in an S domain. They call it the Laplace domain. And you can do regular calculus in the Laplace domain, even on these functions that have discontinuities and points of non-differentiability. And then you can bump back over to the T domain, and it works insanely well. You can turn a non-differentiable function into a differentiable function, do calculus on it, and then turn it back, and you have answers that work. So improper integration is going to be super important. It's not just some anomaly. Like there's some of these things in calculus that you look at that, are cool, but in practice you don't see them a lot. This is not one of those things. Improper integration you're going to see again and again. So definitely spend some time on it, especially because we have a test in 1 week. A week from today, test. So worksheet due tonight at midnight. Review all day Tuesday. So come in Tuesday with lots of questions, and we'll go over them. Trig sub, improper integration are the hardest ones. Integration by parts usually is not too bad. So practice up. I will see you all on Tuesday. Have a good weekend. Steady hard. Steady hard, steady long. Oh, is it not showing? Oh, I'll put it up. Okay, yeah. Thank you for pointing that out. Yeah, it looks like, yeah, I will put that up there for you.
That's like the last thing.
Yeah.
Because the pre-lab is still